Okay. Okay, so first of all, as usual, let me thank very much the organizers of the conference, not only for organizing this conference in this difficult time, but also for their very warm welcome and for their help, you know about solving some issues I had. So I will talk about point-contact spectroscopy in iron-based superconductors, but with a focus on the insight into the pairing mechanism that this technique can provide. Well, indeed, point-contact spectroscopy is known as a technique to investigate the number, the symmetry, and the amplitude of the order parameters in superconductors. However, it also allows to detect some signatures of the boson of the coupling between electrons and the boson that mediates superconductivity, provided that that coupling is sufficiently strong. Here I will report some results on 1111, 122, and if I have time, 11 families of iron-based superconductors, and I will show that in all these cases, these results bring strong support to the fact that the superconducting coupling is mediated by spin fluctuations. This is now rather well accepted by everybody, but it was not when we started with these measurements many years ago. Well, this is the list of people involved in the present work. First of all, the members of the group in Torino, Renato Gonnelli, Mauro Tortello and Eric Piatti, who carried out the measurements and the data analysis, Giovanni Marino, who carried out the calculations within the Lasberg models, and Nicola Barbera and Tony Sciroca, who are not actually from Torino, for the NMR measurements in praseodymium 1111. This is the list of people who kindly gave us the crystals and the films of different kinds. So 1111, 122, and 11. Okay, so what is point-contact spectroscopy? We have already heard somebody talking about this, Professor Naidyuk. This is the standard setup in which a sharp tip of a metal is gently pressed against the superconductor, and the technique is rather simple in principle. It just consists in measuring the differential conductance of that junction. Actually, to obtain spectroscopically meaningful signals, we need to ensure that we know the energy with which the electrons are injected in the S side. So this means that they do not have to scatter in the region of the contact. And this means that the side of the contact has to be smaller than the inelastic mean-free path and of the coherence length. If it is also smaller than the elastic mean-free path, much better, because there is no diffusion in the sense scattering, in elastic scattering. Then we actually used another setup, which is the so-called soft technique, in which instead of the tip we used a small drop of silver paste. Clearly, the small means of the order of 50 microns, so certainly this is not in these conditions, but fortunately we can anyway see spectroscopic signals, and the reason is that we have several parallel nano junctions between individual grains in the paste and the contact and the surface of the material. This is a picture, I don't know whether it is clear, so this is the wire, the gold wire stretched across the sample, and the sample is very tiny crystal mounted there. To be honest, in some of the measurements I will show, we did not use the silver paste, but simply the direct contact between the gold wire and the superconductor. So what is under reflection? Very briefly, so suppose you have a normal metal in direct contact with the superconductor. Direct contact means suppose that there is no potential barrier at the interface, then you apply a bias voltage to the junction and you obtain a current. What happens at the microscopic scale? The electrons that have an energy which is smaller than the gap on the superconducting side cannot propagate as quasi-particles, clearly. So there is the formation of a Cooper pair and the whole is reflected back. This is under reflection. While the electrons that have a sufficient energy to be transmitted in the superconductor are simply transmitted as electron-like quasi-particles. In these particular conditions, what we expect is just a doubling of the conductance due to the fact that here one electron comes but two electrons go away with respect to the normal state. So this is the normalized conductance, which is the ratio of the conductance measured in this configuration to the conductance of the same contact when this bank is also in the normal state. Now, actually, in the general case, there is a barrier here, and so we have other two phenomena possible. So the one is the simple reflection back of the electron, and the other is the transmission of the electron as a hollow-like quasi-particle in the other side. All these four processes are taken into account within a model given by Blondar, Tinkham, and Klapwick already in 1982, in which the superconducting state superconducting state transmission probability can be calculated as a function of the probability of under reflection and the probability of normal reflection. These two quantities contain the amplitude of the gap, of course, and this, once divided by the normal state transmission probability, gives exactly what the normalized conductance, which is actually what we measure. Now, the 1D BTK model, the one I mentioned, has the simple drawback that it is one-dimensional. So, in the sense that the electrons are injected along the direction of the normal to the interface. To account for anisotropies in the order parameters, we have to switch to a more general model that was proposed by Kashiwai and Tanaka already in 1996, in which actually we can account for the fact that the superconducting order parameter is anisotropy, because we account for the fact that the electrons actually cannot be injected with all the directions with respect, all the angles with respect to this normal to the interface. Today I will not talk about anisotropy superconductors, because all the ones I measured were in the S plus minus state, so we will anyway use this one because it is more general than this. Okay, these slides are just made here to show that point contact spectroscopy is sensitive to the symmetry of the order parameter. This is these are spectra in an S-wave gap superconductor, so this is zirconium boron 12, and these are spectra taken in plutonium cobalt gallium 5, which is instead a D-wave superconductor. You clearly see that they are completely different, and this is due to the fact that in this case, depending on what is the angle with which you inject the current with respect to the lobes of the D-wave gap, you can obtain different kinds of spectra. Now, in the case of multiple gaps, which is the case of iron-based superconductors, there is nothing special actually. As in the case of NGP2, it was shown that the total conductance can be calculated within the model by calculating first the partial conductances associated to the different bands that host the different gaps, and then summing them by using a suitable weight. This weight actually depends on the shape of the Fermi surface and on the direction of current injection, but in the absence of clear information on either of these two quantities, it is just an adjustable parameter of the model. Now, we know that in tunneling spectroscopy it is possible to see the signs, the footprint of the strong electron boson coupling. In the case of lead, the boson is actually a phonon. This is the tunneling density of states, and you see that it deviates with respect to BCS because there are some wiggles. Okay? These wiggles are produced by the alpha square f, so by the Eliasberg function of the boson. In this case it's a phonon. To understand how this can happen, let us start from a very simple example. Suppose that the phonon spectrum consists of only one peak, and we have to calculate to understand how this peak can give rise to structures like this. Well, this happens only in the case of strong coupling, so we cannot use the BCS theory, we have to use the theory for strong coupling superconductivity, that is the Eliasberg theory. Within the Eliasberg theory, the gap is not a number, is not a constant, but is a function, it's a complex function of the energy that has an imaginary and a real part. So, with this, we can solve the Eliasberg equations. We get the gap. This is the real part, and this is the imaginary part. With this gap, we can calculate the DOS and the density of state, and it turns out that the DOS has really a structure that is the remainder of this. But what we do is the inverse. So we start from the experiment, and we want to extract information about the phonon spectrum, the boson spectrum more in general. The way is very simple, because actually, if you take this curve and you calculate the derivative, you obtain, and you change the sign, you obtain exactly that. So the idea is that you start from the spectrum you measure in tunneling, you calculate the derivative, that it means the second derivative of the current with respect to the voltage, and you obtain the information of the phonon spectrum. Does this work only in tunneling, or it works only also in the regimes where we have anti-reflection, so low barrier? It works also in the case of anti-reflection. Indeed, these are the spectra for lead, that means the tunneling conductance, calculated for different values of this Z. Z is a measure of the height of the potential barrier. So Z high means tunneling, N, I, S junction. Z equal to 0 means instead no insulator, NS. So you see that there are clearly these structures, and if you calculate, and in the tunneling regime, you calculate the second derivative, you obtain this black curve, which reflects exactly the alpha square F of lead. But if you change the value of Z, you arrive even to the Z equal to 0. You do not have a perfect correspondence, but at least you have structures, at least a peak, whose position more or less corresponds to the energy of the peak in the initial spectrum. So what we are doing now is exactly this. So we start from curves that are in this regime, and we will extract the information about the boson that is responsible for the pairing. Now let's start with samarium 1111. These are very old measurements in polycrystals and also single crystals. The doping is 0.2, so we are on the top of the dome. These are some spectra. Okay, when this paper appeared, we were in the middle of a single gap to multiple gap debate, and we showed that if you use a single gap fit, clearly you can fit these features here, but you leave out most of the curve. So a two gap fit is possible, and it provides reasonable good agreement with the curves. If we put together the values of the gaps extracted from these curves, plus the values of the gaps extracted from very many other curves, and also you put together single crystals and polycrystals, well, you have this picture. Clearly, since we use different crystals, different samples, we have to normalize here and here. So this is actually 2 delta over KTC as a function of T over TC. Here I also, these are also your data, Yuri, these ones. These are the fit, to get fit of your beautiful data, very early data on samarium. And there is a substantial agreement, okay? But you see that the uncertainty is huge, especially here. So as far as the small gap is concerned, it's more or less okay. But the large gap seems to be very large, with the large uncertainty. So we asked ourselves, but is that really a gap, or these are electron-boson interaction structures? Well, to answer this, we have to solve the Hillenberg equations. Actually, we already knew that the most likely boson was a spin fluctuation, so we actually take into account this. We wanted to demonstrate to see whether the boson spin fluctuation can provide these structures here, or instead these are really gaps. So, the Hillenberg model. Well, in principle, the Hillenberg model is for one single band requires solving two coupled equations. One for the gap, which is an energy, a function of the energy, and one for the renormalization function. It can be shown, I don't go too much into details, that for these iron-based superconductors, the minimum, the simplest model you must use is a 3-band model, but with strong coupling. Because if you use a 2-band model, no, it doesn't work. If you use 3-band models or 4-band models with coupling, it doesn't work. So, but 3 bands means 9, in principle, we should need 9 electron phonon spectral functions, because phonons are still present. We cannot neglect them in principle. 9 electron spin fluctuation spectral function. 9 elements of the Coulomb potential, and if we want to be very precise, we want to include also the scattering. We have 9 elements of the scattering rate matrix and 9 elements of the magnetic. Well, it's impossible, of course. It's we absolutely need some simplifying assumption. Well, the assumptions are the following. First, we have 3 bands. For this compound, we chose one effective hole-like band around gamma and 2 electron bands around M. We assume that the gap symmetry is S plus minus, and so these gaps are isotropic individually, but they are negative, and this is positive. This is the line of nodes. Then, The electron-phonon coupling, we know from literature that it is very small in these compounds, and it is of the order of 0.2. So we have to simplify, we disregard it completely. We assume that electron-phonon coupling is absent. Then spin fluctuations are present instead. But spin fluctuation cannot provide intra-band coupling, because within a single band it would be pair breaking with S-wave gaps. So they can only couple the bands that are here with bands that are there. But they do not couple the band 2 with the band 3. So this again is 0. And in the end, we have this matrix of lambda values that are lambda 1, 2, lambda 1, 3, that are these ones shown here. And in principle, I should have lambda 2, 1 and lambda 3, 1 that are actually connected to these through the ratio of the density of states of the bands. Then, what about the boson, the spectrum of the boson? We know that from measurements of inelastic neutral scattering, the chi-second, that means the imaginary part of the spin susceptibility, has a peak that has this shape in the normal state. This was not obvious, because in the normal state it has a very completely different shape. So this resembles a Lorentzian. We chose a Lorentzian shape, so we chose the spectrum to have a Lorentzian shape with a certain maximum at a given energy. What is the energy? Well, we know from this scaling law of the resonance energy in the spin with respect to Tc that there is a, if we want 50 Kelvin of Tc, we can choose an energy of about 20. So we will choose this as 20. Then Coulomb pseudopotential. Well, Coulomb pseudopotential is always difficult to handle. Nobody knows exactly how to calculate it. We know that it is small in these compounds, and for the time being we'll fix it to 0 as well. So in the end we have only two parameters, lambda 1, 2 and lambda 1, 3. That means these two, these two, okay? And with these two values we can fit two things. We chose to fit the Tc and the small gap, which is the one we will know better, okay? And it turns out that the other two gaps are here. So these are not electron-boson interaction structures. These are really the two gaps. We see only one because it is difficult to distinguish, but there are two. And now, but are there electron-boson interaction structures in these curves or not? Yes. These are the electron-boson interaction structures at higher energy, so about 27 and 40 millielectron volt. Indeed, if you take this curve, the black curve, which is the experimental data, and you calculate the second derivative of actually the derivative of this, you change the sign, you obtain this curve here. And at different temperatures, you see that this has peaks that move in energy. Okay, if now we go back to this, we take the energy functions that give the gap, we put them into the big machinery of the BTK model into this, so we calculate the spectrum. It turns out that we have this result, the red curve. The red curve is very good because not only it fits the gaps, but it also fits this peak here and this anomaly, that is the excess of conductance at high energy, which is, for those who work in the field, is the absolutely crazy when you have to normalize the curves, because you don't know how to normalize the curves. But anyway, if you take the derivative of this red curve, you obtain this dashed line here that reproduces the peaks at about 40 millielectron volt. Note that 40 millielectron volt is nothing but the maximum value of delta, which is about 20 in this case, plus the position of the boson, which is 20. Okay. So we don't know why we do not resolve this smaller peak, but this is still unknown. Probably it is due to the fact that the real shape of the spectrum is not simply Lorentzian; it is something slightly different. Okay, in 1 to 2, please can you tell me when I have 5 minutes left, please, Chairman? Can you tell me when I have 5 minutes left so that I can? Okay, so this is another compound of the same family. So this is praseodymium 1111, which is particularly interesting because here you have the spin density wave due to the iron ions, but you also have an ordering at low temperature of the praseodymium ions. So it is particularly interesting to see what happens here. We are already in the region where in principle no long-range order should exist, and in principle, large spin fluctuations should exist because we are very close to this interface. And that spin fluctuations are strong and exist there is told us is given by NMR data. If you have questions about the NMR data, don't ask me, ask Tony, because he made measurements. So in really few words, what we see is, if you look at the line, you see that there are two maxima that slightly merge into one. And you see that the position does not change, at least in the normal state. Then there is a small shift to a higher energy, and the width, that means is slightly broadened. All these things together point towards the existence and the increasing importance of spin fluctuation, not only of the iron but also of the praseodymium. That does not order, because there are no abrupt changes, so there is no long-range order. And if you look at the spin lattice relaxation rate, you see that this is a regular. This is 100 Kelvin, I think. Yes, I don't remember. You see that there is forget it. It's a function of temporal. There is an increase in the 1/T1 when you go down in temperature. There is a peak that actually occurs slightly above Tc. The reason why this is suppressed, it's in principle it should continue to grow, but it is suppressed for some reasons that have to do with superconductivity, according to this model here that has been also used in another 1111 compound in this paper. Anyway, spin fluctuations are there. Let us look at the spectra. Well, this is one temperature dependence of a spectrum. You see that the critical temperature of the junction is the one where the curves recorded at different temperatures start to overlap. You don't have any longer something that is decreasing. Everything is constant. And this temperature is of the order of 24.5 that falls very cleanly at the middle, more or less, of the resistive transition, and is also in agreement with the magnetization transition. The curves these are some spectra with very different resistance, from 180 to more or less 9 ohm. And you see that despite this very large range of resistances, there are structures that fall always in the same points. You see, these are likely to be related to the small gap. These are likely to be related to the large gap, and there are still other structures. Okay. Now, we have other spectra. If you try to fit the spectra, this is in a spectrum rather nice, okay? You can try to fit the whole spectrum, including these wide shoulders, but what happens? First, the gap you obtain is 15.6. Incredible. 2 delta over KTC is of the order of 15 is incredible. So this is a first hint that this may not be a gap. But if you look, if you zoom here, it turns out that the blue curve is unable to grasp this change of slope, which is instead important because this occurs at low energy and this is likely to be a gap. So if you want to fit these two parts, and if you don't want to use a 3 gap, because 3 gaps means a lot of parameters, so 2 gaps are enough, more than enough, you are forced to leave these parts out. So these are the 2 gaps, and these are again electron boson interaction structures. These are other examples in which the 2 gaps are much more clear. You see one gap, the other gap, one gap and the other gap, and these are electron boson interaction structures. If you plot the gaps as a function of the resistance, you see that there is no clear tendency, and this is important because this tells us that we are very likely to be at least at low temperature in the spectroscopic regime. But if you want to if you look at the data, you see that the small gap is rather well defined. The large gap, not so well. And in principle, looking carefully, it seems that, that there might be 2 different, let's say, areas where the gap are concentrated. Now let us see what Eliasberg equations tell us. Again, the same machinery. I do not repeat anything. So now we choose the boson frequencies to be in agreement with this. That means 10 millielectron volt. We use the same shape, the same structure of the Fermi surface, and we get these 3 gaps. Perfect agreement. Almost embarrassing. but this is the case. So clearly 2 are negative, but of course we in this spectroscopy we only see the absolute value. And now let us see whether these the gap functions that provide these values can reproduce these wide shoulders. And the answer is of course yes, because this is the curve generated with the gaps, not BCS, but the gaps that are functions of energy calculated within the Hilsberg equations. This was the gap, the fit with BCS. Okay, this is instead it's not a fit. It's just a calculated curve with that more or less resembles this one. But you see that this usual excess conductance is reproduced. Clearly, for those who work in the field with a slightly different normalization, I could obtain the curve that is exactly this shape. But we did not do that expressly for not to trick. Now in 1 to 2, same story. Here we have single crystals at this doping, and if you look at the spectra, again you have one gap, one other gap probably, and something else, and this something else is very likely to be an electron boson interaction structure. The gaps I have more or less this value, so 4.4 and 9.57. Again, there is a large uncertainty. We can calculate. By the way, this is the temperature dependence of the gaps extracted from this curve. Again, we can look at the problem by using the same approach, but the inverse. So now we do not assume the energy of the boson, but we look directly at the second derivative. This is this curve black here is the derivative of this. This one is a derivative of another contact that might be what is it? This one. No, sorry, this one. And you look at them, and if you plot the positions of the peak, you obtain these 2 red series of points. But now we know from what I've seen in samarium that the peak occurs at omega 0 plus the maximum delta, and the maximum delta is of the order of 10 here. Now we can subtract the gap. So from these points we subtract the gap obtained in this curve. That means it was about 8. So from here we go here. In this case, we subtract the gap that was of the order of 10, so from here we go here, and you see that this is the temperature dependence of the bosonic frequency. That is, of course, not identical, but at least in agreement qualitatively with what expected from inelastic neutron scattering. Then, here I have something which is around 12, more or less. Let us choose a function that is peaked at 12. And we compare this with the scaling law, and it is not so far from what we found, what reported. Then let us calculate the gaps. The gaps are here, 1, 2, and 3. You see, but the one in the middle has nothing to do with your measurements. Yes, it is true, but it is surprisingly similar to that measured by ARPES. So it is possible that we see 2 gaps, ARPES sees 2 gaps, but they are not exactly the same. For sure we see both the small one, but the large ones that pertain to different electronic bands for some reason are not well resolved. So I calculate the values of, these are the values of the gap here. These are the functions of the gaps, so real and imaginary part for all the 3 bands. I calculated the spectra, I calculate the second derivative, I obtain that the points are the second derivative of the experimental curve. The line is the second derivative of the theoretical curve. So there is a very good agreement. Again, if I make the average over 5 different contacts on the same kind of sample, I obtain this curve, this is the second derivative, and I could compare it directly with the alpha square f, that means with the Lorentzian I chose, and they fall exactly in the same position. So this is a rather convincing proof of the fact that either way you see it, you start from the boson and you calculate the spectra, or you start from the spectra, you calculate the boson, you obtain a rather good agreement. I also have data, but I think I do not have time, in iron, selenium, tellurium. These were films and single crystal with 3 different dopings, very fast. These are the spectra, same story. apparently here there are only two gaps. Apparently, if you look at them. So there is one here and something there. But this something there is dubious, because in some contacts we had instead evidences of 1, 2, and 3 structures. So these are likely to be the gaps, and this that does not show in all contacts, actually, but here it is very clear, and here it is very clear, and here it is very clear, is the electron-boson interaction structure.
Dario,
In single crystal. Sorry?
How much time do you need? Your time is over.
No, okay, I can finish. So in the end, in crystals, even better, because the electron-boson interaction structure are well separated. We can do the same thing, so it turns out that these are the gaps, and this is the electron-boson interaction structure. That the fact that this is the real boson interaction structure is confirmed by using the same approach, and we can see that this is the curve generated within the Eliasberg theory. It is not made to fit a curve or an experimental one. It looks more or less like this one. And the fact is that this was generated with a gap of 3.4 and a gap of 2.9. So only this is the gap. These are electron-boson interaction structures. But if we do what we had done at the beginning, so if we think to fit all the curve as if also this was due to a gap, we obtain exactly, this is 8.6, this is 8.5, this is 3.3, and this is 3.7. So the fact that there are boson structures does not prevent a determination of the small gap. So I'm done. So I hope I have convinced you that point contact spectroscopy, even in the under reflection regime, can be used to extract information about the boson that mediates superconductivity, and this can be, of course, particularly useful when you explore new, strong coupling materials. Thank you very much, and sorry for being long.
The question, please.
Okay, very nice and very elaborated analysis of the data. Just to understand, yeah. So generally, there are two things: gaps and electron-boson interaction. So you more now focus on the boson interaction here in your talk.
Yes.
Because to my understanding, in these kind of materials, the gaps probably can be much safer resolved by our angular resolved photoemission spectroscopy, because you have this K-space resolution which we do not have here.
Of course,
yeah?
of course.
But then you are lacking this information on boson. So this is the main advantage of these techniques, that you have both combined without many kind of resolutions which we would like to have, but it's impossible. But you have both gaps and bosons. Exactly. This is the message, because in ARPES you do not have bosons present.
Exactly.
Okay, thank you.
We can, of course, this technique cannot compete with ARPES, especially because first, we cannot associate a gap to a band. We don't know to which band a gap pertains, first. Second, ARPES is, well, in some sense, it's much more powerful, in the sense that you have a direct measurement. However, the technique used to interpret the data from ARPES sometimes gives rise to a large uncertainty also on the gap, because you know, they always have reasonably a very large uncertainty. In our case, at least the small gap has a smaller uncertainty, and we also can see as initially it was a sort of side product, something that okay was that, but then we realized that it was important, because especially when the orbital fluctuations towards spin fluctuation or other boson was very alive, this was clearly in favor of a spin fluctuation mediated superconductivity. Yes.
More questions? I have a question. You spent a lot of efforts in you take into account the multiband character, the strong coupling using the Eliasberg equation. Still, there is a deviation between ARPES data and the point contact data between BTK and this. Maybe this deviation, the disagreement, simply be due to the fact that ARPES is a momentum resolved, right, measurements, whereas point contact measurements is momentum averaged, and actually the real Fermi surfaces, spectra, and gaps are presumed to be anisotropic along the gamma z direction and in the plane. Maybe this simply explain the disagreement.
Yes, well, first of all, the data from ARPES I reported here are already an average over the Fermi surface, as reported in the original papers. So they already took into account. In some cases, you're right. There was some, especially in barium 122, there is a fourfold slight modulation of the gaps in ARPES. This was already the uncertainty. The error bars already took into account this modulation. So these are taken from. It is true that actually, here I did not show, but if you really want to take into account the shape of the Fermi surface in point contact, it is possible, but it is very complicated because there is a model that we developed, which is the three-dimensional BTK model. In principle, this allows you to take into account any shape of the Fermi surface. I don't want to discuss this.
It's possible, but it's hard.
Yes, especially it's very hard for calculations.
Yeah, I understand. Any more questions?
Yes, I have a question. You published this data already 10 years ago, probably, yes? During the time, there is some real tunneling measurements which show this electron boson feature. STM experiments or something like.
But you are saying that it's a question whether
yes, if there is measurements, real tunneling measurement by STM which sees this electron boson interaction feature.
Well, I confess that I can have missed some literature, but personally I'm not aware of. Personally, I don't know. Maybe yes, but I have not seen anything. But actually, the last I made a survey of literature because the last results, the one on praseodymium, have been published right now, so in 220. So I already went through all the literature, and I did not see anything. Maybe there is. I cannot say no.
Okay.